dingy or dusty, anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn.
So this is, believe it or not, the very first program I wrote using a programming language called Scratch. It's a graphical programming language that was developed by MIT's lifelong kindergarten group, and it was designed initially as an environment with which to get students excited about computing, about technology, especially in after-school programs. But what's wonderfully exciting about it, too, is that it's also wonderfully instructive when it comes to what programming is. And indeed, we'll be able to use this programming language ultimately to explore the whole world of programming. Now, what is programming? So programming is ultimately about making software. And software, of course, is what runs on our hardware, runs on our computers. Software is something you double-click and then see and can interact with. Software is the files that you open on your computer and interact with. And software ultimately is what is written using programming code. Now, the software itself ultimately runs on any number of devices. It might be your desktop PC or your Mac. It might be your iPhone or your Android phone. But at the end of the day, all of those devices are programmed by a human writing, quite simply, code. Now, what is code exactly? Well, at the end of the day, code is really just a technical implementation of algorithms, where algorithms themselves are step-by-step instructions for solving some problem. Now, what kind of problems might we want to solve? Well, let's consider an old school one first. Now, this here is an older technology, an old school phone book, inside of which are thousands of names and thousands of numbers. But it's a wonderful opportunity to think about a problem that we might want to solve, like looking someone up in a phone book so that you can actually call them. Well, suppose I'm actually looking for someone like Mike Smith. Now, I could find Mike Smith in any number of ways in this phone book, assuming he's actually in here. I might initially start very correctly and very foolishly, perhaps, at the first page, looking down for Mike. I don't see him. So I move to the second page, look down, and I don't see him. At the third page, and so forth. And as I proceed through the phone book, I do claim that this algorithm, this set of instructions, step by step, for solving this problem is correct, because if Mike is here, I'm going to find him eventually. But of course, this is completely ridiculous. This is a completely inefficient algorithm for actually finding Mike Smith. Why? Well, it's going to take me forever to find him if he's all the way toward the end of the phone book. Now, wait. I know how to do this faster. I remember from grade school an old trick where rather than counting by ones, you might count by twos. So here I might do 2, 4, 6. Literally. This algorithm turns out is much slower. 6, 8, 10, 12, 14, 16, 18, and so forth. And at that rate, I'll certainly find Mike much faster, twice as fast, in fact. But is that algorithm, are those steps correct? Now, they're not quite correct, because what if by chance I happen to be grabbing 2 pages and Mike happens to be sandwiched in between them? I might blow right past Mike's name in the phone book. So I better have at least a check, a sort of condition where I think to myself, wait a minute, if I hit someone whose name starts with T instead of S, maybe I should double back at least 1 page. Now, of course, no one out there, if you even still use this technology, is going to solve this problem in that way. What are you going to do instead? Well, if you're like me, you're probably going to instinctively go roughly to the middle of the phone book and look down there to see where you are. Now, odds are, if you're like me in this book here, you're going to find yourself in the M section. But Smith, of course, comes after M. And so we know Mike is to the right side here. And so that suggests that we could take a pretty big bite out of this problem. I don't need to start flipping 1 page at a time. I know Mike is not in this half of the phone book. And what's nice about this intuition is that, you know what? I can, not only figuratively, but shall we say, tear this problem in half. That wasn't really very hard at all this time. Throw half of the problem away, and I'm left with just 1/2 of the very same problem fundamentally. Now, what might I do? I don't want to resort to the slower approach. I, again, want to leverage that intuition, divide and conquer this problem, and look down and realize, oh, I'm in the T section. I went a little too far, but no big deal. Let's tear the problem in 2/3 and really in half. So I'm left with just 1/4 of the problem now. And of course, I can repeat this algorithm again and again and again until theoretically I'm left with just Mike's number on this one sheet, or in this case, one scrap of paper. So what have I really done there? So the intuition ultimately is that rather than looking for Mike 1 page at a time, I'm instead leveraging the fact that that phone book is sorted. And I'm literally dividing and conquering the problem again and again and again, so that if I started with 1,000 pages, I then go down to 500, I then go down to 250, 125, as opposed to starting at 1,000 and going to 999, then 998, 997, which surely is going to take me much longer. Now, of course, that's not the real way to tear a phone book in half. So fortunately, there are just 2 of these phone books left on Earth, and we have the second one here. So indeed, if I want to go ahead and tear a problem in half, the real way you do this, shall we say, there we go, is that way. But now back to some programming. So I just solved that problem, but what was the algorithm exactly that I used to solve it? In fact, can we distill some of the key components of what I did fairly intuitively and see if we can't then later apply those same principles to solving other problems altogether? Well, let's consider this. I propose that the very first thing I did was this in step 1, I picked up the phone book. Step 2, I opened to the middle of the phone book and I looked at the names. But then I had to make a decision because I was at that point presented with some information as to what is on the page. And so step 4, if Smith is among the names on the page, then step 5, I was going to call Mike. Else if, step 6, Smith is earlier in the book, that is, he's to the left alphabetically, well, then logically I should open to the middle of the left half of the book and then go back to step 3, thereby looking at names again and continuing down this same set of steps. However, if after step 6 I decide, no, Smith is not earlier in the book, and therefore I should not do steps 7 and 8, well, then let me ask the question, else if Smith is later in the book, that is to the right of where I'm currently looking, and if so, open to the middle of the right half of the book, and then go back to step 3, because now I'm looking at a different page and a different set of names. However, if that's not the case that Mike's among the names, and it's not the case that Smith is earlier in the book, and it's not the case that Smith is later in the book, then what should I do perhaps in step 12? Well, else, or otherwise, I should in step 13 just quit. Because logically, if Mike's not on this page, and he's not to the left, and he's not to the right, then he must not be in the book at all. And so what do we have here? Well, this is something that I would call code. It's not written in C or C++ or Java or some other programming language you might have heard of. It's written in English of some sort, pretty succinct, terse English. And indeed, it doesn't follow any particular vocabulary. I just tried to say each of these lines as succinctly as I could. So we'll call it pseudocode, sort of code-like syntax that happens to be written in English, though you could write it in most any other language. But what's important is a few characteristics. One, just to keep things nice and orderly, I've numbered the lines. Now, I did that manually. Software can certainly do that automatically for us. But that helps me make sense of what comes after what. And in particular, it also allows me in steps 8 and 11 to make these back references and sort of go back to and re-execute some earlier lines. But there's also some similarities, I'd argue, among some of the verbs and some of the language here that I've used. Let's see if we can't highlight a few of those principles. So one, notice here in yellow are a whole bunch of actions, a whole bunch of verbs that are telling me to go do something. Pick up, open to, look at, call, open, go back, quit. Those are all very specific procedures, or we'll call them functions, shall we say. Now, what else is sort of similar among these lines? Well, here I have if, else if, and else. Let's henceforth call those conditions or branches. They're decision points. This is really a four-way decision point, and I have to go down either this road or that road or this other road or this fourth road when making a decision. But what do I use as input to make that decision? Well, let's consider these questions really that we're asking ourselves. Is Smith among the names on the page in front of me? Is Smith earlier in the book? Is Smith later in the book? Well, a programmer would call those three phrases Boolean expressions, named after someone by the last name of Boole. And a Boolean expression, by definition, is either true or false, yes or no. So it's really a question that has a yes, no, or true, false answer. And indeed, each of these yellow phrases has an answer because I use that answer, yes or no, to decide whether or not to execute some subsequent lines. And in particular, notice that only if those Boolean expressions, and ergo the whole branch is to be taken, is true and is to be taken, then only should I execute lines 5 and 7 and 8 and 10 and 11 and 13. And notice per the indentation that those lines are very deliberately associated with exactly those conditions. So you only do them if the line above them is true or is yes. Now, lastly, there's this curiosity. And both line 8 and line 11 go back to step 3. Well, henceforth, let's start calling this a loop or a cycle, because conceptually, that's pretty much what's happening. I'm being told in steps 8 and 11 to go back to some earlier step. But given that I came from that step, this is indeed a loop in the sense that I'm going to keep doing perhaps the same thing again and again, maybe going left, maybe going right, hopefully eventually exiting or calling Mike, because I've deliberately induced some kind of loop here. But these aren't the only ideas that we might see in a computer program. And indeed, that's what that was. When finding Mike Smith in that phone book, that was effectively a computer program being executed by me, albeit a human. But the code or the pseudocode that drove my thinking and drove my actions is exactly the same kind of logic that you might feed to an actual computer, whether it is a PC or a Mac or an iPhone or an Android phone, because what computer programs tend to share in common, no matter the language they're written in, are things like functions and loops and conditions and Boolean expressions, and even more features still, things called variables and threads and events, and even more features. And so that's what we'll do here and on out, is explore not just programming fundamentals, but explore some of these fundamentals in the context of some actual languages. First, one of the oldest languages someone might know. We're not going to go quite as far back as Fortran and COBOL or binary, if familiar. Rather, we'll start with this one here. This is a small program, just a few lines of code, so to speak, written in an older language called C, a language that's still very much in use, but it's older in that it's been around for some decades now. And it doesn't tend to have that many features, but it's nonetheless a very powerful language on top of which, so to speak, more recent, more modern languages have been built. Now, it looks pretty cryptic. I'll grant you that. There's like this hashtag over there and these angled brackets and curly braces, parentheses, semicolon, \n, and a few other syntactic curiosities. But what do all those mean? Well, even if unsure at first glance, like odds are you are, you can probably take a guess as to what this program does. Suppose I did write this program as such, and then somehow ran this program on my Mac or PC or phone. What's it going to do? Probably. Yeah, I mean, even if you don't recognize all the syntax, I do recognize the word print or printf, whatever that is. But printing, I'm familiar with. And I do see a phrase here, hello world, though I'm not quite sure what that \n is. So I'm going to guess this program, when run, is going to print hello world. And indeed, that's what it does. Now, there's a bit of overhead here, not just syntactically, but sort of conceptually, because you ultimately, as a programmer, need to understand, what does this line do? What does this line do? What do these curly braces mean? Why is there the \n there, and so forth? But those are all just things that you learn. For instance, if you've not spoken Japanese as a language, or Spanish, or any number of other languages, the very first time you look at that written language, it might look like Greek to you, so to speak, and might indeed be Greek if you don't speak Greek. But that's just because you haven't recognized those patterns before. You haven't recognized those symbols before. And indeed, if right now you're staring at something that's completely unfamiliar, and while you do recognize some patterns, it's not all very straightforward, that's just because you don't yet speak the language. You don't yet know the language. You don't yet know how to program in this particular language. But what's exciting about programming in general is that even though there are dozens, if not hundreds of languages, programming languages in use today, they're much more accessible, I dare say, than written and spoken human languages. Rather, you'll find many, many, many similarities among programming languages, such that once you know one and a few, can you relatively easily bootstrap yourself, teach yourself other languages that might have newer and fancier features, and then just therefore make you more productive. Because at the end of the day, that's what programming is all about. It's about writing software and therefore controlling hardware with it to solve problems on your behalf, whether that problem is to make a telephone call on a mobile device, whether that problem is to send an email or search for something on the internet. All of those problems are solved ultimately by controlling hardware with software, and the means by which you do that is by programming, writing code like this that ultimately runs on those devices. And yet, I can't help but recall that the computers I know or grew up with somehow or other only understand zeros and ones, right? They only understand the so-called binary system, and yet this does not quite look like zeros and ones. So how is it that I, who can just barely understand this as a human, can program a computer using this and have it understand this, even though these themselves are not zeros and ones? In other words, how do we get this to that instead? Well, it turns out when writing a computer program, there's often multiple steps. And sometimes these steps are automated, but sometimes you have to make them happen manually. And in general, the process of converting this code here, or source code, which tends to be English-like syntax that does follow a set of standards and use a certain vocabulary, this being C, the language known as C, I can convert this source code to machine code, that is zeros and ones, that look like this, by running this source code through a special type of program quite simply called a compiler. A compiler is simply a program that compiles code, converts it from source code to machine code so that the human can write it, but the machine can ultimately understand it. Now, consider another example here. This program looks almost kind of, well, not really the same, but it's written in a very similar language called C++. Now here too, you might not recognize some of the symbols on the screen, but you probably do recognize hello world, this time apparently without the \n. And even though we have a different word up here, IO stream and standard end L here, odds are it's a pretty good bet that this program too does print hello world. And this is already, in simplest form, testament to the fact that many programming languages do the same things differently. Indeed, whether you know C or C++ or something like Java or PHP or Python or Ruby or any number of other languages, odds are at the end of the day, you can actually solve the same problems using any number of different languages. Much like you as a human can express yourself verbally in any number of spoken languages, but it might just be easier to communicate with other humans in one language. It might just be easier and less time consuming to solve problems using one programming language over another. And this indeed in part explains why there are just so many programming languages. We've seen just 2 so far, but many different languages exist because as more and more time passes and more humans use these languages, do they realize, wow, I could do this better, or gee, I wish it had this feature instead, or wow, I wish I could type fewer keys on the keyboard in order just to have my computer say hello world. And so you'll find that different languages do things differently, even if the end result is the same. For instance, here is a language called Python. And thank God, like this is now the simplest example of the ones we've seen thus far. It really just says what it means. No hashtags up top, no curly braces apparently, just print hello world. And that's indeed what this program in Python does. Now Python, it's worth noting, is a different type of language in most implementations. That is to say, you typically don't write Python source code and then manually convert it to machine code, zeros and ones. Rather, there's a special program that you use that's not called a compiler, but called an interpreter. Because what's also the case with some languages is that rather than convert them directly to zeros and ones that your CPU, your computer's brain, understands directly, you instead convert them to some intermediate language, generally known as bytecode. Java is the same way, as are some other languages. And so with Python, before running this, I might actually compile it or convert it to this much more cryptic looking format. This is not code that I myself would particularly enjoy writing, but this is what's outputted when you write Python code, and it's outputted as something called bytecode. So this is just an intermediate format that still is somewhat readable. It's at least alphabetical characters and not zeros and ones. So as a human, I kind of sort of can read it. But my computer can absolutely read this, specifically a program called an interpreter on my computer that I could download to my Mac or PC or some other device can understand these lines one at a time. And so generally a language like Python might again be compiled to an intermediate language like this here, this bytecode, and then it's this code ultimately that's read by the machine. But the takeaway for us is really quite simply that there are different ways of doing the same thing in any number of languages. And even among those languages, do they get used in different ways? Sometimes you have to compile your code and then run the resulting machine code, the zeros and ones, by double-clicking an icon or typing some command. Or might you be able to write your code and not explicitly compile it, just instead interpret it? The steps might feel or be a little different. But at the end of the day, most users experience the software in a familiar way. by double-clicking an icon, by running the name of a command. And for all intents and purposes, your users or your customers don't need to know or care what language something is written in, so long as it is created for your particular type of computer or your particular operating system. This is why if you have a Mac, for instance, and a friend has a PC, you can't necessarily just share software and run the same programs on multiple computers. You might each have to buy or download different versions of the software, one of which is for Mac OS, one of which is for Windows. And even though those programs might be written in the same language, they've generally been compiled for or packaged for different computers, CPUs, or really different operating systems. But this is just a decision that the software author, the software developer, or software engineer, so to speak, simply has to make on your behalf before shipping his or her software to you. Now, what about other languages? This one here is Java. It too has some syntax of its own, but at the end of the day, it's going to do the same thing. Print out to the screen just hello world. This example here is another language called Ruby, which is commonly used as an alternative to some of these languages here as well. And it is even more simple syntactically in this particular example, in that it's going to put or print on the screen hello world as well. This one here is written in a language called Lisp, the salient difference here being these parentheses on the outside, which are just hinting at a syntactic feature of this particular language. But this is quite simply how you might print hello world. And then in another language altogether, JavaScript, is this how you might print hello world to the screen or browser window as well. Now, we've certainly only just scratched the surface of these several languages. And surely these languages can do much more. And odds are it's going to take many more lines of code. But throughout each of these languages are some commonalities. Support for things like functions and loops and conditions and Boolean expressions and maybe things like events and threads and variables and more. And so rather than get too much into the weeds of very specific languages, let's focus here on the ideas. And let's focus on these ideas as graphically and as pleasantly as we can by revisiting that first programming environment called Scratch. In particular, you'll recall that Scratch just a moment ago was raining trash down on my screen in synchronization with the old Sesame Street song that you might remember. But how was that program working? Well, consider how we might have gone about implementing some of these basic ideas. There was trash falling from the screen. Well, what does it mean to fall from the screen? Well, a screen, recall, is just a grid of dots, a grid of pixels, a bunch of pixels left, right, a bunch of pixels top, down. And so to move on the screen or to animate something on the screen really means just to take an image, whether it's a PNG or GIF or JPEG or some other format, and just move it slightly, maybe one pixel downward at a time. And if you move that image downward one pixel at a time quickly enough, it doesn't look like some very jagged movement. It, to the human eyes, actually looks like a very clear movement. And so indeed, what I was probably doing in order to make trash fall from the sky here is it started off screen, and then in some kind of loop moved some number of pixels every second or every split second. And the result is some animation. Well, why does the trash, like the shoe and the piece of trash, actually stop at the bottom of the screen? Well, odds are I could solve that problem with some kind of condition, some kind of logic or Boolean expression where I ask the computer, if you're touching the bottom of the screen, sneaker, then stop moving. Or conversely, only if you're not touching the bottom of the screen should you be moving top to bottom. So you can effectively stop the animation by just using some additional logic and asking a question, are you at the bottom of the screen, yes or no, true or false? Meanwhile, every time I clicked and dragged a piece of trash into the trash can, what was happening? Well, Oscar was emerging from his trash can, which was another form of animation altogether, but he was also shouting out in a little cartoon bubble the number of pieces of trash that I'd already deposited in his can, starting at 1, then 2, then 3. Well, he would appear to be using something you might recall from algebra, being a variable, like x or y or z. And this variable was probably initialized or set initially to 0, because we'd put no pieces of trash. And every time Oscar received a new piece of trash, he probably incremented or added 1 to that variable. So 0 becomes 1, which then becomes 2 or 3. Now, how did I increment that variable? Odds are there's some kind of condition saying if piece of trash added to trash can, then increase the variable's value by 1. If it's called x, make x 1, then 2, then 3. So again, a basic building block. Now, there was more and more trash that would eventually fall from the screen. And my God, there's that song that I still can't get out of my head some 10 years later. But that, too, was playing on some kind of loop or some kind of synchronization with the game at hand. So even if at first glance this game seems pretty daunting, and you might think, wow, that must have taken you like, what, David, 8 hours? Well, that is true. It did take me at least that long. And I swear, by far the most challenging aspect of this game wasn't getting the logic right, but was getting that song in of and henceforth never out of my head. But the key takeaway is that all of this seeming complexity, if you kind of zoom in and focus conceptually on just individual aspects of this game or this computer program, can be reduced to just conditions and loops and variables and some basic building blocks. And I dare say if you think about the software you yourself use every day on your phone, on your laptop, or your desktop, odds are, even if you might have no idea how a browser is implemented or no idea how Excel or Word or Keynote or Numbers or any number of other programs are written, odds are if you really focus on just small pieces of that software, individual features, could you probably start to glean exactly how the software developers who made the software actually implemented those features. So let's now break down Scratch into some of its fundamentals and start applying some of these very ideas. Here is perhaps the simplest of programs that you might implement with Scratch as a language. Surprise, surprise, this is how in Scratch you would say, hello world. Now, in the world of Scratch, you have a graphical environment where there is, as we'll soon see, a cat that actually performs all the actions. So much like I, the human, was performing these actions with the phone book just a bit ago, in the world of Scratch, by default, is a cat going to perform any of the commands that you provide in software. We can change the cat to anything else. Indeed, I turned him into Oscar in that example. But this is what the commands themselves are going to look like. And Scratch, as we'll see, has a whole bunch of fundamentals. For instance, Scratch is going to have functions or actions or verbs that look a little something like this. Like this is a puzzle piece, purple in fact, that's going to specify that Scratch should say hello world. Here's another puzzle piece that, as you might guess, is going to tell Scratch to say hello world forever, again and again and again in some kind of cycle. Meanwhile, in Scratch, this is how you're going to repeat something a fixed or finite number of times, 50 in this case. This in Scratch, though a much bigger block, is how we're going to specify things conditionally. If x is less than y, then do the following. Else, if x is greater than y, do the following instead. Else, third fork in the road, do this, some other thing altogether. And so indeed, you can really see in this example that Scratch, being graphical in nature, actually has you programming not by typing words alone on the keyboard and numbering your lines, as I did earlier with the phone book algorithm, but rather putting together puzzle pieces whose shape kind of implies what they do. The fact that this if block kind of looks like this, and inside of that block you can put other blocks apparently, implies that you should only say that x is less than y if it's inside of this if else block. And now notice we have apparently crammed another if else block inside of this to effectively create a three-way fork in the road. And in green here, do we see some Boolean expressions asking the question, is x less than y or greater than y? In these two lines here. And then in orange, do we have variables, x and y themselves, which are probably just numbers. So how do we go about assembling all of these building blocks into actual programs written in this language called Scratch? Well, let's go ahead and run the Scratch software itself. Scratch is not only a programming language, it's also a whole programming environment, a piece of software unto itself that's going to allow us, by dragging and dropping these puzzle pieces, to program the computer. Well, let's take a look at the user interface, or UI. At the top left here is Scratch himself. He lives in this two-dimensional world that has a height and has a width, and currently by default has just this blank backdrop, and he can move up, down, left, right, and do many more things in that environment as well. What kinds of things can he do? Well, in the middle of this user interface, do you see a whole bunch of palettes or categories, these being the scripts, and these blue blocks here all fall under the header of motion. So these are all puzzle pieces or blocks that somehow relate to Scratch's motion. Meanwhile, if we click through costumes, we could change the aesthetics, and in fact we could turn Scratch into a dog or to a grouch. And under the sounds tab, could we actually explore sounds and multimedia that we can integrate into Scratch. But the blank slate with which we begin is this big area over here on the right, to which I can drag and drop these puzzle pieces and actually interconnect them in order to instruct Scratch to do things. For instance, let's try. Now, I just know from having used Scratch before where some of these blocks are. And in the first one I'm going to grab is under Events. And I'm going to click and drag and grab this one here, which is titled When Green Flag Clicked. Because if you didn't notice before, notice now that above Scratch's two-dimensional world here is not only this blank background, but also this green flag in green signifying go, and this red stop sign signifying stop. And it's by clicking either of those buttons that I can start or stop, respectively, any program here that I write. Very similar in spirit to double-clicking an icon on your desktop or typing a command in a prompt on a typical computer. So meanwhile, I have now this when green flag clicked block, and I want Scratch to say something. Well, I know from having used Scratch before that the say block happens to be under looks, where a whole bunch of puzzle pieces are as well. And notice what I can do now is click on say hello, where hello is just the default word. And then notice here, if I drag, notice how it turns white and kind of glows when I move the block close enough as though they're magnetized. Well, that's because these two blocks want to logically snap together. So as soon as I release my mouse button, will they lock together as such. And now I can double click on the text box there and type hello, comma, world, and actually type any number of words that I might want Scratch to say. Well, let's zoom out, move my cursor over to the green flag, and click, and voila. The first of my programs. It's doing exactly what I said. And indeed, notice it's not stopping to say hello world anymore because I never actually had a command that said, hey, Scratch, stop saying hello. And so I'm just going to manually stop this program for now with the red stop sign up there. All right, so that's all fine and good, but it's not all that realistic. Cats do not have speech bubbles coming out of their mouths. So let's make it a little more realistic by moving up here to my blocks, clicking and dragging and pulling away the say block. And I can just let it go anywhere in the middle, and it will just disappear or be deleted. And now this time, let me go up to, say, sound. And oh, this is promising. Play sound meow is a purple block here. Let me go ahead and do this. And notice it, too, has a very similar shape, even though it's a little longer. And it wants to interconnect as soon as I let go. Let me go ahead and zoom out and click now the green flag. Aww. 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 So Scratch has just meowed 3 separate times because I ran the program 3 times by clicking on the green flag 3 times. Now, that's a little tedious, and it's also not very lifelike if every time I want to hear Scratch, I have to sort of breathe new life into him by clicking the green flag. Wouldn't this be an opportunity to leverage one of those principles we looked at already, that of a loop or a cycle, if I want Scratch to do something again and again? So for instance, let me go ahead and poke around under the control blocks, perhaps. And oh, there's that repeat block. It defaults to 10, but we can change that to anything I want. And if I click and drag here, now this isn't quite right logically, because I don't want to play the sound meow when the green flag is clicked and then repeat something 10 times. So you know what? I'm going to just leave this in no man's land for just a moment. I'm going to click and drag this purple block away so it becomes detached. And now notice, you might think that it definitely is not going to fit inside this repeat block. That's just not too tall of a space. But notice that the whiteness is, in fact, illuminated, kind of saying, yes, this is OK. And the shapes do kind of match. And so what's nice about Scratch is that so long as the shapes are in accordance, can you let go, and the containing block will grow to fill that particular shape. And even though it looks like we're now completely out of room within that repeat block, we could actually drag and squeeze more and more blocks there, and the block will grow to fill. So let's just do this 3 times. And now let's go ahead and connect this to the when the green flag clicked. Zoom out, click the green flag, and Now, I am pretty sure logically this says when the green flag is clicked, repeat the following 3 times, play sound meow. And yet, unless I'm not hearing things right, I only heard 1 meow. So what's wrong? Is this a bug, a mistake in Scratch? Did MIT screw up? Or is this a bug in my code somehow? Did David screw up? Well, let's consider the options. Let me go back to that sound category and see if there's maybe a different block I should be using. Now, I'm only just now reasoning through this, right? Because I've written a program that I think should do one thing. I have realized it did not do what I intended. So is it my fault? Is it the software's fault? And maybe am I misunderstanding the functionality of some of these blocks? Now, what do you notice here? Scratch supports drumming, apparently, and other notes. But up above, it can play sound meow. Or more precisely, it can play sound meow until done. What happens if I use that one instead? Let me try. Let me go ahead and drag this one away to effectively delete it. And then drag this one in its place so it too still fits. Now let me go ahead and click that green flag. Interesting. That time I did hear it all 3 times. Let's just be sure. OK. I definitely heard it all 3 times that time. But why? Well, with the previous version, which I'll restore here by going back to the way it is, notice that the program was actually performing correctly so far as the definition of these blocks go, just incorrectly with respect to my own expectations. Computers, recall, are really fast, right? This Mac here might be a gigahertz, 2 gigahertz fast, which means it can do 1 or 2 billion things per second. And that's a lot. I mean, I am by far the limiting factor as the human in this equation. So maybe, just maybe, Scratch was literally doing what I told it to do, which was when the green flag is clicked, repeat the following 3 times. But Scratch, being a computer program, is just so fast, it played the song or the sound 3 times, but it played it so fast within this repeat block that all 3 of those meows were effectively overlapping. So we only heard 1 of them because all 3 were being played pretty much at the same time because that loop was going around so quickly. But by contrast with this other puzzle piece, play sound meow until done, now I'm compelling the program to just give me a moment to listen to the entirety of that sound before you proceed to the next iteration or the next cycle, and then one more pause until the next cycle so that I can hear it 3 and exactly 3 times. So such a simple program and such a simple example. And odds are, whenever you're writing code and it doesn't behave as you intend, and you look at it and you think, no, that is right. That's not necessarily the case. And indeed, bugs or mistakes in one's code are going to be perhaps one of the most common and one of the most frustrating experiences one has when first learning to program. But these are the kinds of things that with practice go away. And so unlike I just did, you reach instinctively here on out for the right block as opposed to the incorrect one. Now let's see what else we can do here when it comes to sound. What about not just playing a sound, but adding a bit of, shall we say, animation here? Well, how might I go about making this cat move? Well, let me go ahead under Control and do something forever, because I just want this cat ultimately to move back and forth forever. That, of course, involves motion. So let me go to Motion. And all right, I like the sound of this. Move 10 steps. And 10 steps is probably going to be 10 dots or 10 pixels on the screen. Well, then what do I want him to do? Well, let's see what happens first if I click the green flag. OK, so not quite what I intended because he's not really moving anymore. And this is actually a feature being designed for aspiring programmers and not to mention children. Scratch kind of realized, or rather MIT realized, that in designing Scratch probably shouldn't let the cat go 100% off the screen. So we can just kind of click and drag him back into view here if we want. But of course, program's still running, so he's just going to run away from us anyway. So how do we fix this? How do we make him go back and forth without me have to manually intervene? Well, what about some kind of condition? Let me poke around, say, the control blocks, and let me actually grab one of these conditions. And instead of moving 10 steps forever, again and again, after making 10 steps, let me ask a question. Am I touching the edge? Because if so, I don't want to keep going. So to ask that question, let me go under Sensing here. And indeed, let's see, this one here, touching, sounds about right. But I don't want this to have anything to do with the mouse pointer or the cursor, but rather with the edge. So by this dropdown, let me change this Boolean expression to touching edge. Drag and drop this over here. And this certainly doesn't seem to fit size-wise, but shape-wise it does. So if I let go, the block, as expected, grows to fill that particular Boolean expression. And now what do I want to do? Well, now maybe if I'm touching the edge, I should turn some number of degrees. 15 doesn't feel quite right. I want to turn all the way around. And I know that to be 180 out of 360 total possible degrees. And now let's see what happens when I click the green flag. OK, so better. He's not just running off the screen. And now I don't have to click and drag him back into view. But of course, turning 180 degrees isn't quite the visual I want. We don't really intend for the cat to be flipping upside down. So maybe there's a better way. This definitely a bug aesthetically, but perhaps not functionally. But there's still an opportunity here. Let's leave that bug alone. Let's pause the program with the red stop sign here. Let me go into sounds just for fun. It's hard to justify this academically here. But let me go into the sound bar where you can hear not just the default meow, but you can also click on the microphone. And let me go ahead and give my best example of cat running into the side of a screen. Ouch! And stop that. And you can now see a waveform or a graphical depiction of what my voice apparently sounds like. Let me go ahead and click and delete the moments of silence beforehand and also a little after. And interestingly, it seems like I really mustered some energy and then said ouch, but we'll leave the rest of the wave together. I'm going to go ahead and name this recording ouch. And now notice if I go back to scripts and I go to sound, now ouch is available from the drop-down as one of my sounds. And let me go ahead and put that not outside the condition, but inside, so that now if I'm touching the edge, not only do I want to wrap around 180 degrees, I also want to play this sound. Let's see what my newest program now sounds like. Ouch! Ouch! Okay. Ouch! OK, maybe not very cat-like. Ouch! A bit more like ouch! Human hitting the edge of a screen. Ouch! But it is correct, that 180 degree detail aside. And so notice what's guided my building of this program. I didn't set out and drag all of the possible puzzle pieces at once. I didn't record the sound in advance all at once. I instead took the proverbial baby steps, very small incremental steps, starting with something very simple, just a forever loop and just have the cat move all the way to the side of the screen. Then did I add to that the feature where he would actually wrap around conditionally in the form of that if block. And then did I go in and add the third feature, which was this silly human ouch-like sound. But the key takeaway there is that it's much easier, I'd argue, to write complex programs if you start off by breaking them down into those component parts and consider individual milestones for yourself. So how you might set out implementing just one feature at a time as opposed to everything. And indeed, if you consider real-world software that you use on your phones or your computers, certainly did Microsoft not set out to build in one day an entire word processing program called Word or an entire spreadsheet program called Excel. Odds are their software developers back in the day, the very first version of this software, did they write just one small feature? Maybe you double-click the icon and it just opens a big rectangular window that does nothing, but at least they had the beginnings of the software. Then maybe they added support for just a column, maybe two columns, maybe any number of columns and any number of rows. And so there, too, Microsoft, among other companies, have set milestones for themselves such that the end result is impressive and amazingly complex, maybe even millions of lines of code in C or C++ or Java or some other language. But they didn't start out by trying to tackle that all at once, just like I, when starting out this program, did not set out to implement it all at once. Now, with that said, let's open a couple of examples that have already been written and see what they do themselves. This, then, is Pet the Cat, a program I wrote in advance that still stars Scratch and already has these puzzle pieces assembled. So what does this do? Well, let's go about reading code, which is another side of software development. Most software programs, certainly the largest of them, are not written by single humans, but rather by teams of humans who are collaborating. Indeed, even though you might have the mindset or the expectation that programming is largely a solitary exercise done late at night with lots of caffeine and darkness and a flickering computer screen, the reality is it's an incredibly collaborative profession. It's an incredibly collaborative hobby for some, whereby you work either alongside a whole team of individuals or remotely with a whole team of individuals collaborating at whiteboards, collaborating virtually, and ultimately reading each other's code, not only to understand what someone else has written, but to enhance what he or she has done by building atop their own lines of code, or in this case, their own puzzle pieces. So let's try exactly that, and let's read this code that I've already written. When green flag clicked, forever do the following. If touching mouse pointer, then play sound meow, and then wait for 2 seconds. If touching mouse pointer, then play sound meow, then wait for 2 seconds. So what's this program going to do? Well, its title kind of gives it away. But if I click the green flag, nothing seems to be happening. But notice that all these puzzle pieces are now highlighted in yellow to indicate that the program is indeed running. But nothing's happening until, let me move my mouse pointer over the cat. Let's try that again. Interesting. So this time, rather than meowing forever, Scratch is only meowing when my mouse pointer is touching him, just like this. So this is kind of like the digital equivalent of petting the cat. Well, what about the opposite? What might it be like to write a program wherein you don't want to pet the cat? Well, for that example, let's open Don't Pet the Cat, which now looks like this. So this program's a little more complicated in that it has not just an if block, which asks one question, but an if-else block, which asks a question and then behaves one way if it's true and another way if it's false. In this case, we forever, if touching the mouse pointer, then play sound lion 5, so like the 5th of our lion sounds until done. Otherwise, play sound meow and then wait for 2 seconds to give the human a chance to sort of orient himself or herself and pet the cat again. So let's see what happens here. But consider that I've induced this time an infinite loop forever. Yeah, there's the meowing every 2 seconds. OK. What about not touching the cat? What was the imperative there? Let's try moving the cursor closer. 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 That is why you don't want to pet the cat. So in that case, did the lion sound only play when the cat was actually touched with the mouse pointer? Well, what about variables? What about programs in which you actually want to count something, as in the case of the sheep? Now, of course, in our human world, it's often we humans who are doing the counting. But let me propose that it's sheep who deserve a chance to count themselves sometimes. And so here we have counting sheep. And indeed, this is literally a sheep counting. And how is he doing that? Well, over here, since I've already clicked the green flag, do you see highlighted the program that he's running? When green flag clicked, he set counter to 0. So this orange puzzle piece is like a custom piece that I made in advance via the data palette. And it allows me to create a variable called anything I want, x or y or z, or frankly, more descriptively in English, counter, because what it is, I want a variable, something that stores a value, that does counting. I'm going to call it counter instead of the more generic x or y or z. And then I'm forever going to do the following. I'm going to say not hello world or some other phrase, but rather the value of the counter. So I seem to have dragged and dropped the variables puzzle piece right on top of the say block for 1 second. Then I'm going to wait for a second. Then I'm going to increment the counter by 1. So change it by 1 by adding 1 to its value. And then just keep doing this forever. And so the sheep is now going to count up and up and up and up and up, seemingly forever. If that gets a little boring, I suppose we could always remove the wait block and just have the sheep count again and again and again and again. And so now there's no blinking effect because the speech bubble isn't going away, but the number is indeed counting a little faster because we're saying it for 1 second at a time. But it's one thing to use puzzle pieces that MIT has created for us, these conditions, these loops, these variables. What if my programs start to get sophisticated enough and my ideas start to get grand enough that I'd really like to start creating my own puzzle pieces that maybe MIT didn't envision programmers needing? Well, it turns out in most programming languages, you can do exactly this. You can create your own custom functions or procedures by assembling new functionality out of other existing puzzle pieces. And so in this way, can we use existing puzzle pieces, kind of wrap them up with a new name, with a new shape, and actually then give that shape a name so that henceforth, I don't have to worry about using all of those individual puzzle pieces. I can use just one newly named one to achieve some goal. Let's consider the following example, cough 0. This is an example, per the puzzle pieces up here, that simply instruct the cat to cough 3 times, waiting a second in between. Say cough for a second, then wait. Say cough for a second, then wait. Say cough for a second, then wait. Of course, if I click green flag on here, you're going to see, as you might expect, the cat is unfortunately coughing, not once, not twice, but 3 times in total. This is clearly now an opportunity for better design. And indeed, you can see the surface of an opportunity for better programming. This is not a good design. It's a correct design in that it will say cough 3 times and wait a second in between. But it's not a very good design because it kind of sort of looks like I copied and pasted these puzzle pieces, much like you might do with your own word processing program or email client or the like. I've just taken a couple of puzzle pieces and said copy, paste, paste. And maybe I'd do it even more if I wanted Scratch to cough more than 3 times. But we can do better than that with programming. We can, of course, use loops instead. So in cough 1, do we have an alternative example wherein the cat now is going to cough 3 times, but by way of a repeat block, a loop. Now, the code is functionally the same, but this would be arguably better designed because now if I want to change what the cat is saying, or when he's coughing, maybe I want to spell it differently, or I want him to wait some number of seconds that aren't just 1, well, I can just make a change in one place rather than in like 6 different puzzle pieces. I can focus on just the one instance here. But suppose that it's coughing that is the puzzle piece that I want to create and use here on out, so I don't have to remember that that is how you make a sprite, a character on the screen cough. Because in addition to having one cat like this, we can actually have multiple cats, or a cat and a dog, or a cat and a dog and a grouch, or any number of other characters. So this is to say it would be nice, once I figure out how to do something in a programming language like Scratch, I'd really like to save that functionality in a custom function, in a puzzle piece that I have made, so I can use it elsewhere, not just for this sprite or cat, but for others. So in cough 2, do we now have an example that defines a new puzzle piece called cough. It's purple in nature. I grabbed it from the More Blocks palette. And you'll notice that I've defined with this special puzzle piece a new piece called cough. Beneath that block is a number of statements. Say cough for 1 second. Wait for 1 second. And that's it. But now above this is my new program. And this is where things get really interesting, because now I can drag and drop when green flag clicked. I can still grab a repeat block and do something 3 times. But what do I want to do 3 times? This time, I just very simply want to cough. And so now, thanks to my custom puzzle piece being defined here, I now have access, under More Blocks, to a custom puzzle piece called cough that not only says what it means, which is nice and descriptive and easy to use, it also hides, or so to speak, abstracts away all of the underlying implementation details, or the complexity, relatively speaking, of what it means to cough, so that all I or a friend who's using this puzzle piece has to worry about here on out is that the puzzle piece is called cough. Does not matter how it's actually implemented. And it turns out that in programming languages, just like Scratch, you can make one additional improvement on this. Rather than have to rely on your own repeat block, notice what else you can do. In this case, I've refined my implementation of this custom puzzle piece, cough, to take what we'll call, and what a programmer would call, an argument or a parameter, some number of inputs that influence the behavior of the puzzle piece. Now, we've seen arguments or inputs all over the place thus far. Move some number of steps. That's an argument or a parameter. Say something. That's an argument or a parameter, because it influences the behavior of the move block or the say block, respectively. So how do I do that? How do I make a cough puzzle piece that doesn't just cough once, but coughs 2 times, 3 times, 10 times, however many times the user of that puzzle piece wants? Well, I would use the puzzle piece ultimately like this. And notice there's now a little white box where I can type a number. But it turns out you can parameterize your own custom functions by using a special puzzle piece like this that has not just the name of your custom function, but also a placeholder for a variable, really. Variable being another way of thinking about a parameter or argument. And so what I've done with n, and I'm just calling it n for number, but I could have called it anything I want, x, y, or z, or something else, I can now repeat in the implementation of cough that many times. I don't have to hard code 3 anymore. I don't have to hard code any number. I can drag and drop a copy of n here so that whatever number the user of my puzzle piece types in, that's what will be used for the repeat block, and that's how many times this puzzle piece will say cough and wait 1 second. And so this now is just a small example of what it's really like to program and solve problems. The problem, to be fair, is relatively small here in that we just want the cat to cough visually on the screen. But the opportunities that that problem affords really are captured in these several examples. With these examples, do you see me starting out in the simplest, most naive, and correct way possible? But it wasn't very well designed because I was just kind of duplicating the say block and the wait block, and then the say block and the wait block and the say block and the wait block. It already sounds tedious, and indeed, it's poor form. But then I factored that out with the repeat block, and then I introduced a custom puzzle piece whose second version also allowed me to parameterize it. And so the fun in programming and the opportunities to become a better programmer are illuminated with examples like this. To be good at programming is to notice opportunities like this, to actually take opportunities like this, to factor certain common code out, to abstract it away or bundle it inside of custom puzzle pieces or black boxes, so to speak, is what's evidence generally of not just correct code, but good design and well-designed code. Now, these are just a few of the features you might see in a language. There's certainly a few others too. Let me go ahead and open up an example here called thread. And you'll see, as promised, Scratch's support for multiple sprites, multiple characters. And this is the funny thing. Because thus far, almost all of our programs, indeed all of our programs, have had just one cat or one sprite, and therefore really one thread, as we'll call it. They're only doing one thing at a time. With this example, per the cat and the bird, this example will actually have two things happening at once simultaneously, and there's some kind of interrelation between them. Notice that the cat is kind of stealthily and very predictably following the bird. This is not random, but oh, no, please, getting not exactly what we were hoping for there. So there was clearly some kind of interaction or dependency there. So what was going on? Well, notice that the bird is highlighted in the bottom left, as has been our cat previously. And so this at top right is the program driving the bird's behavior. When the green flag was clicked, it went to -150 and +150. It turns out that that blank world in which Scratch lives can be addressed with coordinates, x and y. So some number of pixels left or right, some number of pixels top and bottom, and I just decided arbitrarily to start it at -150, 50 with some trial and error. I then had it point in a 45-degree angle just because, so it starts off in an interesting way. And then I forever told the bird, do the following. If not touching the cat, the other sprite, then move 3 steps, and if on edge, bounce, which is a nice one-line version, one single puzzle piece version of the if construct we did earlier, where bounce means turn 180 degrees, but I've used a puzzle piece that comes with Scratch to achieve the same result. So that's it. If the bird is not touching the cat, then just move 3 steps. And if you're on the edge, bounce. So just keep bouncing around. Just keep moving. So the bird doesn't put all that much thought into what it's doing. The cat, meanwhile, is kind of clever. The cat, when the green flag is clicked, goes to -160, -160. So I made sure that they don't start too close to one another. I then have him point in a random direction. Scratch, like a lot of languages, supports random or pseudo-random numbers, where just like a human can pick a number, like 50, that's kind of sort of random. So can a computer pick a number between 91 and 179. And that, you might notice, is between essentially a 90-degree window. And that's because I wanted the cat to at least start off at some range of angles. Then I wanted the cat forever to do the following. If you're touching the bird, play sound lion 4 this time, then stop this script. So I wanted to make sure that the cat didn't keep moving if it touched the bird. I wanted the game just to stop, or the animation to stop. And so I explicitly say stop so that the human doesn't have to click the red stop sign. But then, here's the cleverness, forever point toward the bird and move 1 step. So the cat has this very stealthy advantage that no matter where the bird is, and remember, the bird is kind of bouncing every which way, bouncing randomly off the walls ultimately, the bird is very slowly but surely tracking, the cat is slowly but surely tracking the bird by always pointing toward it and moving 1 step. And so even as the bird is sort of aimlessly flying around, the cat is very slowly but very methodically, very algorithmically, if you will, pointing itself toward the cat. So if we rerun this program, you'll see the cat's indeed exercising exactly that logic. And the bird's kind of getting away, but again, the cat is pivoting to follow him. And he keeps going and keeps going and keeps going, and we'll again find him right there. Now, of course, we could give maybe the bird a bit more of an advantage. Let me go ahead and click on the bird. And how about instead of moving 3 steps, let me have him move 6 steps, twice as fast. Click the green flag. Very nice. So the cat is still moving at the same rate. Unfortunately, it's still moving toward the bird, and the bird is not taking that into account. We could give the advantage to the cat instead. So if I go back to the cat script, and instead of moving 1 step, how about 10 steps? And let's see what happens now. Cat pretty much seeks out the bird, a bird-seeking cat. How about one more example that speaks to the height of the ceiling with an environment like Scratch, just how much you can do using some basic fundamentals. This time we have a couple of our puppets here to star. Notice one is blue, one is orange, and one is playing Marco Polo, it would seem. If familiar, this is a game that kids might play whereby if one person says Marco, the other kids are supposed to say Polo, and then one is supposed to find the other in that particular game. But we're just using it as an example of something called events. So it turns out, per the last example, that a computer can effectively do multiple things at a time thanks to multi-threading, where a thread is an independent thread, so to speak, of execution that is happening in parallel with something else on the computer. And especially nowadays, now that computers have multiple cores or CPUs, they can literally do multiple things at once. And even if they can't, computers are so much faster than us humans that even if the cat and bird aren't technically moving at the same time, even if the cat gets to move a bit and then the bird, the fact that that's happening so quickly means my human eyes probably won't even notice. So for all intents and purposes, a multi-threaded program is indeed doing multiple things at once, just like our past example. But sometimes those threads might want to intercommunicate, not just pointing themselves at each other, but actually sending messages. And notice how this can work. When green flag is clicked, let's have this puppet forever do the following. If the key space, so the space bar is pressed, then say Marco for 2 seconds, as per this game, and then broadcast something called an event. An event is like sending a message wirelessly that only computers can hear. So it's not saying just the word Marco. It's also transmitting a signal called an event. And so long as the other puppet has been configured to listen for that event, then it can respond to the first puppet's action. So the orange puppet is going to say Marco and then broadcast this so-called event. The blue puppet, quite simply, is going to do this. When I receive event, say Polo for 2 seconds. So in other words, this blue Muppet is not going to do anything when the green flag is clicked. There's no such block there. Rather, when I receive event, that secret wireless signal from some other sprite, in this case the orange Muppet, the blue Muppet is going to say Polo for 2 seconds. And so notice the dependency we've created between these two guys. When I now click on the green flag, nothing appears to happen. But the orange Muppet, remember, is listening for my space bar. And so as soon as I hit it, he says Marco, and the blue guy hears it and says Polo. But the only thing listening for my key press is the orange puppet. The blue puppet, meanwhile, is only responding to the event emitted by the orange puppet. Now, this, of course, allows us to implement this simple little game with puppets. But this idea that one thread can convey a message to another is what's ultimately compelling. Surely I could use that, maybe in more complicated programs, as a mechanism for having two sprites interact somehow. Not just follow each other around on the screen like the cat and the bird, but maybe exchange messages of some sort, so that something only happens to one sprite if something has just happened to another sprite. Whew. Well, that was Scratch. Now, this is, of course, just one programming language, and it's graphical at that. And indeed, programmers in the real world don't typically write software by dragging and dropping puzzle pieces. Rather, they write textual lines of code, like the C and C++ and Java and Python and Ruby code that we saw earlier. But the ideas that they write down and the ideas that they leverage are functionally identical to so many of the ideas that we've seen here in Scratch. What Scratch does for us for our purposes here is just get rid of things like the hashtag symbol and the curly braces and the parentheses and so many other syntactic features that are really just distractions and necessary for the language's vocabulary, but not necessary to understand the ideas. So if you walk away today with an understanding of what functions are and loops and conditions, Boolean expressions, variables, and perhaps threads and events, and some of the other features we've seen evinced by Scratch, do you have really a fundamental understanding of what it tends to be like to program in fairly common languages. Indeed, we focused on one type of programming language here, imperative or procedural programming, and there's other worlds out there. There's object-oriented programming, there's functional programming, but at the end of the day, the key takeaway is that in these languages are there generally these principles, these fundamentals, these building blocks, as embodied by literal puzzle pieces here, with which you can assemble solutions to problems by using very small problems solved with these puzzle pieces and build on top of those solutions even more and more sophisticated solutions still. In fact, consider, after all, where we began, looking at Oscar time. That is a game where you have to rack up as high a score as possible by clicking and dragging and dropping trash that's falling from the sky into the trash before the game ends. But what does that even mean? Well, again, if you zoom in to the lowest level at the puzzle pieces and the building blocks that compose that program, well, there was just a loop that was making the trash fall. And there was just a variable keeping track of the score. And there was an if condition raising the lid of the trash when the cursor got close enough. And so all of the complexity of that particular game at the end of the day can be reduced to these and other basic primitives. As to what other languages are out there, this is just a slice of the possible list. But on the screen here, would you see some of those familiar ones again, C and C++, but so many others that are being used currently or have been used in the past. And the ... suggests that there's so many more. In fact, if you'd like to take a look on Wikipedia and be completely overwhelmed by the many languages out there, you'll be impressed by just how many we humans have created over time. But at the end of the day, there tend to be trends in this industry. And when you are a programmer or a software developer or a software engineer in the real world working for a company or really just working for a hobby, well, you as a programmer tend to have just one or a few languages that you tend to reach for. So becoming a programmer is not about learning that list of programming languages. Even I only know a tiny fraction, probably count them on one or two hands in total. But you tend to want to introduce yourself to different types of programming languages so that when something new comes along or some new device comes along that you want to program for, you have the basic ideas and principles in mind and simply need to pick up a bit of new syntax. And as such, it's a little bit easier, I dare say, than learning a new spoken or written human language, because these languages tend to be more narrowly defined with fewer keywords, but the ideas persist even as some of those particulars changed. Now, to wrap for now, I thought we'd take a look at an oldie but goodie, a program written by one of our own former students that synthesized music, synthesized loops, synthesized conditions, all to create a wonderfully animated conclusion to this look here at programming.
We're your weather girl. And have we got news for you?
You better listen.